Hello students, in this lecture we are going to discuss about simple harmonic oscillator. Okay, okay. So we have already discussed the simple harmonic oscillator in our last two lectures, but this will be the simple harmonic oscillator in the operator formalism. Okay. So now we are all familiar with the Schrodinger's formalism, okay, of quantum mechanics. So what we do in Schrodinger's formalism, we write your Hamiltonian, okay, minus h cut square by 2m, okay, d square by dx square plus half m omega square x square into psi n of x is equal to your energy eigenvalues into psi n of x. So this is nothing but a Schrodinger equation, okay, and we are all familiar with this Schrodinger equation. Okay? There is an alternative formalism which is now very much famous, and most of the advanced textbook of quantum physics deal with that formalism. That formalism is Dirac formalism. Okay. Basically, this here you can see that we have a differential equation and we have to solve a lot of differential equations. This is basically more on matrices, okay, and so in this formalism the Schrodinger equation can be written like this: h psi is equal to e psi. Okay, this is the Schrodinger equation. In Dirac formalism. See, what Dirac formalism says is that any operator, okay, any operator like a Hamiltonian operator or any other operator can be represented with a matrix, okay. So this is your operator, okay. Any state, okay, can be represented, okay, with a column vector, column matrix. Okay, when the operator operates on this, it will give you an eigenvalue, okay, and again this thing, okay. So this is your operator, okay, this is your column matrix, okay, this is nothing but your wave function, okay. So this wave function can be written as a column matrix, your operator can be written as a kind of square matrix. This is nothing but a number, okay, which is we call it as eigenvalue, and this is again your wave function psi, okay. So you must be familiar with, in mathematics, the eigenvalue equations, okay. So there also we are having a matrix which operates on a column vector and it gives you an eigenvalue, and then you move ahead. So this is nothing but an eigenvalue equation, okay. So this is nothing but an eigenvalue equation, and this eigenvalue equation is the crux of this Dirac formalism in quantum mechanics. And almost any kind of problem in quantum mechanics can be treated as an eigenvalue problem. And basically, we design an operator. We write that operator in the matrix formalism. The wave function can be written as a column matrix. And when we operate this, we find the eigenvalues, as you most of you must have learned in your linear algebra course or in basic mathematics course, that how to find eigenvalues of a system. And okay, so this is what this thing is. This notation in which I have written the psi must be new to you. This is known as ket notation. Okay, so this is known as ket psi. Okay, this is known as, I will pronounce this as a ket psi. Okay, for every ket of psi, there exists a complex or a Hermitian conjugate of psi, and I write this as this thing. This is known as bra. Okay, and I will call this is bra notation. Okay, so these are very important, that the wave function is generally written as a ket, and for every ket there exists a bra. Okay, so if you are having a column matrix 1 minus I 2, okay, so this is your ket psi, and for ket psi you can write your bra psi, and bra psi will be equal to, okay, since it is a column vector, the Hermitian conjugate of this will be a row vector. You have to write the first entry will be 1, the second entry will be the conjugate of this thing, so this will be I, and this is 2. So for every ket there exists a bra, and this is how you can write. Okay, I will not go in the details of linear algebra right now. Okay, since the main aim of this topic is to just introduce you the formalism of simple harmonic oscillator in the operator formalism. So Hamiltonian is the operator which is responsible for the energy. Okay, so that is your Hamiltonian operator. The states, okay, the states of an simple harmonic oscillator can be labeled as, so this is your ket 1, this is your ket 0, so this is your ground state. So the wave function of ground state can be written as ket 0. The wave function of your first excited state can be written as ket 1. This can be written as ket 2, ket 3, ket 4. Okay, so this is how this thing goes on. So this n is basically the energy level. Okay, the wave function corresponding to the nth energy level. En is actually your eigenvalue of that level. So if I want to find the eigenvalue of this level, the energy of this level, then I have to take the Hamiltonian operator, operate this with this state, and once I do this, I will get the energy of the first excited state. Okay, so this is how this thing works. So for general nth state, I can write, okay, now this is your Schrodinger equation. Okay, now here for harmonic oscillator, we know our Hamiltonian is written as p square by 2m plus half m omega square x square. Okay, so this is your Hamiltonian, and you can also write this is equal to, if I take h cut omega common, then here I will get p square upon 2m into h cut omega plus m omega by 2 h cross into x square. Okay, so these are the important things. Now here if you see, then we are having this thing, we are having this thing, okay, and we are having this thing. Okay. So just for sake of physical understanding, you can see that the dimensions of h cut omega are of the dimensions of energy. The dimensions of 2m h cut omega are equal to the dimensions of momentum square, and the dimensions of m omega by 2h cross will have the dimensions of inverse of length square. So it will be having 1 by length square dimensions. Okay. So you can see that this is your momentum square, and we are dividing it with this quantity of momentum square. So this will be a dimensionless quantity. Okay. This is your x square, and this is having the dimensions of 1 by L square. So L square by L square. So this will again be dimensionless. So H will have the dimensions of energy. Okay. So Hamiltonian operator has the dimensions of energy. Always remember. Okay. Now, okay. So we were at this point where we have written H is equal to H cross omega P square by 2m H cross omega plus m omega by 2h cross into x square. Okay. So again, I will use some rescaling of variables. Okay. So if I use a variable xi equal to under root of m omega by 2h cross into x, and other variable eta is equal to p by under root of 2m omega h cross. Okay. So if I introduce this and this variable in this, so if I call this as equation number 1, and if I call both of this as equation number 2, then plugging 2 in 1 will give me H is equal to H cut omega into eta square plus xi square. Okay. This is H cut omega. So this is your H cut omega. So this is your, okay, let me call this as equation number 3. Okay. Now, if I calculate the commutation relation between xi and eta, then what will be my answer? Okay. So, since you know that xi is nothing but under root of m omega by 2h cross into x comma p divided by under root of 2m omega h cross. Okay. So this, we can take the constants outside. So the constants will be 1 by 2h cross, other things will cancel out, and we will be left with x comma p. Okay, x comma p is a famous commutation relation, okay, which is equal to ih cross. So ih cross divided by 2 into h cross. So this will be I divided by 2. Okay, so xi and eta are non-commuting operators, and the value is I by 2. So as we know that Hamiltonian H is equal to H plus omega into xi square plus eta square. Okay, so if I write H is H cross omega into xi plus I into eta into xi minus I into eta. Okay. So this quantity, okay, and this quantity, okay. So if I write this quantity, so this is a linear combination of two operators, so I define it with some other operator which is I call A. So A can be written as xi plus I into eta, okay. And if I denote with this quantity, this is nothing but a Hermitian conjugate of this quantity. So I can write this with A dagger, okay, xi minus I into eta, okay. So this are our two important quantities. So if I plug in now the values of x and xi and eta in terms of x and p, then your variable A will be under root of n omega by 2 h cross into x plus I under root of 2 n omega h cross into p. Okay. So if I take some terms common, then I can write this as A is equal to n omega by 2 h cross, okay, x plus I into p by n omega, okay. So and this thing can be written as A dagger is equal to under root of n omega by 2 h cross into x minus I p by n omega. Okay. These are very, very important results which you have to remember by heart. Okay. Okay. We are going to use this two expressions a lot. Okay. So I will call this as expression number 4. Okay. So these are our definitions of operator A and A dagger. Okay. These are very famous in various fields of physics, not only when we are talking with a simple harmonic oscillator, but in advanced fields such as quantum field theory. These are very important operators. Okay. So these are our two operators, and these have got very special names. Okay, A is known as a raising operator, a lowering operator, and A dagger is basically a raising operator. Okay, we will know that why we call them as such. Okay, so we have got now the values of A and A dagger. Okay, so if I calculate the value of A into A dagger, okay, then this can be written as, okay, since A we have defined as xi plus I into eta, and A dagger we have defined as xi minus I into eta. Okay, we can expand this and we can write this, okay, xi square, okay, plus, okay, eta square, okay, plus there will be I into eta xi, okay, minus I into xi eta. So this will be equal to your xi square plus eta square, plus I take I common, then I can write eta into xi minus xi into eta. Okay, so you can see that I can write this as a commutating bracket. So this will be equal to xi square plus eta square, okay, plus I into eta comma xi. Okay, so this is your value of A into A dagger. Okay. Now, if I want to find the value of A dagger into A, okay. Now this will be simply the complex conjugate of this thing, the Hermitian conjugate of this thing. Like you know that in matrix we can write AB dagger is equal to B into A. So simply A into A dagger, the whole dagger can be written as A dagger, okay, into A. So I have to just take the Hermitian conjugate of this thing, and this will be nothing but just I have to replace this I with minus I. So this will be xi square plus eta square minus I into eta comma xi. Okay. So if I add both of these quantities, then I will get A into A dagger plus A dagger into A, okay, is equal to 2 times of xi square plus eta square, and so you can find now that xi square plus eta square is equal to A into A dagger plus A dagger into A divided by 2. Okay. Now you remember this expression where we have written H as h cut omega into eta square plus xi square, and now we have found the value of eta square plus xi square in terms of A and A dagger. Okay. So as we know that H was approximated as, okay, h cut omega into, okay, eta square plus xi square, and now since we have the values of eta square plus xi square, we can write now h is equal to h cut omega A into A dagger plus A dagger into A divided by 2. Okay, so this is the value of Hamiltonian. I will call this as result number 5. Okay. Now we can find very interesting results. Okay, so your Hamiltonian operator is now written as h cut omega by 2 A into A dagger plus A dagger into A. Okay. Now, if I want to find a very important commutation relation, which is A comma A dagger, then this is generally written as, okay, so you know that A is generally nothing but m omega by 2h cross x plus I p by m omega comma m omega by 2h cross x minus ip by m omega. Now you have to expand this entire commutator. So I will take the constants outside. So it will be m omega by 2h cross. So if I take the first thing in consideration, then okay, so let me write this in now curly brackets. This will be x with x, so this will be x comma x, okay, plus the other thing will be x with p, so minus I by m omega x with p, okay, and there will be now p with x, so it will be positive I by m omega p comma x, and minus, okay, there will be I square upon m square omega square, but the commutation is with p, okay, so this term is 0, this term is also 0, we have only this term and this term with us, so this is equal to m omega by 2h cross, okay, and x comma p is equal to ih cross, okay, so minus I by m omega into I h cross, so I into I is minus 1, this will be positive, plus I by m omega p comma x, this is minus I h cross, okay, so this is again minus, and so this is again positive, so I have now with me m omega by 2h cross into 2 times of h cross by m omega, and this is equal to 1. So this is a very important commutation relation of A with A dagger is equal to 1. Okay, always remember this. Okay, we will see some interesting results based on these things in the next lecture. Thank you.